In this video, we talk about the derivative as an instantaneous rate of change. We're just going to summarize some of the applications of the derivative and then sort of preview some problems that we're going to work in future videos. So here are some particular examples. So we've got population growth rates, production rates, flow rates, velocity and acceleration as we know. We're all familiar with this interpretation. If we've got y equals a function of x, we can always find the slope of the tangent line by computing the derivative and plugging in that particular x value. What that is going to give us, it's going to be, the limit of the slope of the secant as the distance between 2 points goes to 0, and that gives us the slope of the tangent. We also discussed projectile motion in another video. If that motion is one-dimensional and vertical, where the only acceleration is acceleration due to gravity, and that velocity, initial velocity, is in the same direction as gravity, then that we just have some projectile sort of moving on a line sort of up and down. So maybe we're here and we throw like a ball up with a velocity that's positive, or we are at this location and we throw a ball down with a velocity that's negative, or we just release it from rest. And that's where our initial velocity is 0. Then we would use this equation. And if we're talking about two-dimensional projectile motion, where like if we're throwing a ball from one person to another, that ball has a vertical displacement and a horizontal displacement. The horizontal displacement is given by x, the vertical displacement is given by y. And we use the same equation for y that we used before with the one-dimensional case. And for the horizontal displacement, it's just like the vertical displacement, but there's no acceleration in the x direction. So that term is gone. And this initial velocity is initial velocity in the x direction. This initial velocity is initial velocity in the y direction. That's our initial y value, and that's our initial x value. And last few videos, we also talked about position, velocity, speed, and acceleration. So if s of t is position as a function of time t, we know we can take the derivative of that and we get velocity. This is change in position with respect to time, or the limit as delta t goes to 0 of that average rate of change of position with respect to time. If we take the derivative again, we get acceleration. And if we take the absolute value of velocity, we get a non-negative number, which is the speed. For these types of problems, you might just be given the function and be asked to compute the velocity and the acceleration. And some problems later, you'll be given velocity and be asked to find the position, or be given the velocity and asked to find acceleration, or given one of these and asked to find the other 3. And then we saw in an earlier video that we might be given the graph of one of these, and we might be asked to find the others and then interpret the others in terms of the motion of the particle, the person, the car, whatever it is that is traveling that particular position as a function of time. Then in the last video, we talked about geometric applications where we had just formulas from pre-calculus. For the volume of a sphere, for example, it's a function of the radius. You can take the derivative, and that's meaningful. This is the instantaneous change in the volume as our radius increases at a particular value of the radius. Similarly, the area of a circle has this formula. You can take its derivative, and this would give you the instantaneous change in the area at a particular value of r as the radius is increasing at that location. And this is the example that we used with the volume of the cube in the last video. Now, there are some very interesting applications in our book. I took these problems from section 2.2, but we are going to build on all of this material with related rates and lots of other geometric applications of the derivative in chapter 3, which is associated with unit 3 in our course. We're going to work this modeling data problem in the next video, which is about stopping distance. There's a really interesting fuel cost problem. There are lots of business applications. This one is titled Inventory Management by the textbook authors. And then there are lots of problems involving differentiability and making a function differentiable. We've already looked at one of them. We had that problem or that set of problems involving the sine of the absolute value of x and the absolute value of the sine of x. That's 117 in section 2.2. And then there are a couple of other examples that our sort of geometric problems and choosing values to make our functions differentiable. We're going to do that in another video as well. But all of these have something in common, and they're all dealing with the derivative as instantaneous rate of change. When you see this, when you see that y is a function of x, the derivative can be denoted this way: dy dx equals the limit. We'll just say as delta x approaches 0 of that average rate of change, the change in y divided by change in x. Oh, this instantaneous rate of change can always be interpreted as the instantaneous rate of change of this variable in the numerator divided by this variable in the denominator. It's really just slope. When geometrically it's just slope, but when we're interpreting it in real world applications, we look at the units of the numerator and the units of the denominator to interpret that number, that answer that we get when we plug in a particular value of our independent variable to this function. All right, so that's instantaneous rate of change. I think it's pretty cool because if you can find anytime you have a function of a real variable, we can do this. And you see that there are lots and lots of diverse applications, but we have a tendency to focus on this geometric application and sort of these physics applications in calculus.